Okay, good morning. Good afternoon. Let's start lecture. Okay. We're going to look at design of a shaft example today. Okay. So in previous lecture we have talked about shaft design considerations. So let's look at an actual shaft design example. Okay. So not analysis, but a design example here. Okay? Alright, so this is the shaft we're going to design here. So wait until it pops up. And I'll show you the process for typical process for designing a shaft. Right? There are definitely procedures needs to be iterated. Okay, so here is the shaft. Just like what I said, like the course project, when you design a shaft, the first step is you have to basically plan out the layout of the shaft first, and also plan out the lengths for each sections of the shaft first. So this is just like this example. What's given is you already have the layout, right? So wherever you have a bearing, shaft, a shoulder, a key, okay, or snap ring, or case. So these are already laid out. The lengths are also laid out here too. Okay. The only thing that you don't know at this stage is the diameter. Basically, what will be the diameter for each sections of the shaft, and that's what we need to decide. That's the design part. Okay. Yeah. Another thing is what's known is the loading condition. Okay, you will know that. Okay. Once you know the loading condition, and you can make use of some assumptions first, and then to design for the shaft. Okay. So let's look at this particular shaft that is here. Okay, so a lot of parameters are given already, so I'm not going to list there. So when we calculate, we'll just assume there are certain numbers there now. Okay, yeah. In this particular question, it's given basically. So maybe let me open up the lecture notes that are here. Okay, so horsepower, 2 horsepower here. This shaft speed. Here's the shaft dimensions A, B, C, D's, right? Like what's shown at here. So A, basically A, B, C, D, A, B, C, D. They're all given out here. There is a gear over here, and there is a sheave over here. The gear has a pitch diameter. Okay, it's also given. Okay. The sheaves pitch diameter, okay, and the radius also given over here. Okay. There's a pressure angle for the gear. The sheave has a basically V-belt tension. There's a belt on the end here, so there's a tension here. So F1, F2 are referred to the tension force on the V-belt. Okay. And the ratio is also given. And then there's a 50% of the reliability. Okay, so I'll show you roughly the procedure here without too detailed of calculations here. Okay, yeah. Okay, so first step. Okay, you need to calculate the torque. Okay, so the torque, okay, comes from basically the horsepower and also the velocity, the shaft speed. Horsepower, as we said, is a 2 horsepower, right? And then we use the formula H times 63,025 divided by the revolute per second. Okay, so that'll give us the amount of torque. So this will give us 73.073 for the torque and here. Okay. Okay, the unit is pound-force inch. Okay, that's a standard unit. Whenever you use this formula, that's a standard unit set here. Okay, so then the next step, okay, once you get the torque, and you're supposed to basically know that how the torque is distributed along the shaft, and that we typically obtain that information through sketching what type of diagram? Torque diagram, right? So here is basically what happens here. You have a basically amount of power transmitted to this gear, and then the gear through the shaft, and through the shaft to the sheave here. So that's the output here. Okay, yeah. So basically, if I'm going to analyze the shaft, then I should know that the torque exists only between where and where, only between here and here, basically. Okay, yeah. And also, we're talking about basically a uniform torque, okay, which means your Tm is not 0, which is this much here, okay, and the Ta will equal to 0, okay. So no magnitude, just a constant torque throughout at here, okay, yeah. All right. So second step, okay, when you do the shaft, always free body diagram, right? Free body diagram here. Create a segment line here representing the shaft. By looking at this question here, it made an assumption which I would recommend that you actually don't use this assumption. So basically, it's assuming the width of the bearing to be very narrow. So the supporting force at the bearing location are kind of simplified basically to the edge of the bearing at here. Okay, so the two supporting force, see that? It's simplified to the edge of the bearing. But when you do the shaft design, I would recommend that you use the center of the bearing for more accuracy, basically. Okay, yeah. But anyways, for this one here, let's consider just using this example. So we're going to use these locations for the supporting force, and this is A, this is B. So they're this is actually not B. This is so how about location C location. So A location, C location are the bearing location, right? Okay, so you have A location at here, and then you have a C location at here. Okay, free body diagram. Okay, so let's move this out of the way. So you have a supporting force in both directions. So this is a typical two-plane bending situation, right? Two-plane bending. At A location, you have two supporting force. One is in the XY plane, and one is in the XZ plane, okay, or YZ plane. Okay. So and then let's call this R2Z and R2Y. That's the supporting force, right? Now, the other location of force comes from the gear. So there's probably a small gear pinion on the top pushing it, okay, with a pressure angle 20 degrees. Then there will be a force at this K location here, which is this B location, right? So at the B location, because of spur gear we're talking about here, so you only have two type of force. One is WR, and the other is the WT. Okay, WT. And at the sheave location, which is the output location, so you do have two forces acting on the belt, okay, which ultimately will be acting on the shaft, right? So that two forces, apparently there's no vertical, the two forces always pointing to one direction. So basically at the end at here, which is the D location, Okay, there's only one force, so the direction doesn't matter. Okay, so just don't worry too much about direction. Just, you can always flip that. But that's the overall free body diagram. You see, right? This is the end here. So you have all the forces distributed, okay, along the shaft free body diagram. Okay. So when you do the shaft design, you have to do something like this to find out the loading conditions, right? Okay. So now what we can do is we can trying to figure out essentially what each one of these are, right? But what we have to first figure out is what WR is, what WT is, okay? And also we have to figure out these values at here, okay? Yeah. So the question at here, if you look at the sheave, okay? This is the circle for the sheave. Here you have F1 over here and F2 over here. The radius of that is called RS, which RS equal to 3 inch. Okay. So we're going to make use of some of the given conditions to calculate F1 and F2. Okay. So for this question here, F1 minus F2 times RS. So that's basically, if you use this minus this times the radius, what does it give you? Give you the torque, right? And the torque needs to be balanced with the torque at this location. So the same torque from here to here, and that's this much at here. So that should be T, okay, which is 73.073. Okay. That's the first equation at here. So that gives you F1 minus F2 and equal to T over RS. Okay, that's the first equation. And the second equation, the question has a ratio given to you. So the tension belt F1 over F2 is 5, so we can use that relationship. So two equations, two unknowns, and we can calculate F1 and F2. Yeah, calculation at this stage is not that important. I think you need to be very comfortable with the design process at here. Okay, so but anyway, so this is basically how to figure out F1 and F2. So we'll be able to have a force F1 plus F2. That's basically, now we know that at the D location now, right? Okay. How do I figure out WT and the WR? WT times the radius of the pitch diameter of the pitch circle will give us the torque, right? So that basically we got WT equal to T over RG, and RG is given in the question, so that's 3 inch. So that gives us 24.36 pound-force. That's WT. Okay. What about WR? So if you recall, when you have a gear and W is acting on the gear at a pressure angle 20 degree, and this is your WR, and this is the WT, right? This is WT. Once you know WT, and you can calculate WR using simple trigonometry at here. So WR equal to WT times tangential pressure angle phi. So phi is 20 degree, WT is here, so that gives us 8.87 pound-force. Right. Okay, so that figure out basically all of the external forces from the gear and from the sheave. Okay. Now you can make use of the equilibrium equation to figure out those R1Z, R1Y, R2Z, and R2Y equilibrium equation. There's a software called MD Solid. You can actually easily figure out if you want to resort to some sort of a tools, right? So you can figure out which basically here's the list of numbers for the forces. and it's probably negative right here. Okay. Okay, so once you figure out the forces at here at the different locations, right? At different locations. Now bear in mind, I think there is a software called MD Solid, okay, for you to use. And if you use AutoCAD Inventor, in AutoCAD Inventor there's a design accelerator. You can also actually use that design accelerator to figure out all the supporting force for you. Okay, yeah. Okay, so once from here, this is step number 2 now, right? So step number 3, then you sketch moment, okay, and sketch bending moment. And torque diagram. Okay, so that's this step here. And sketching this diagram, you can also use software to actually help you to do this. There's one tutorial, I think I listed the number of software for you can use. They should be help you, but otherwise you can sketch even yourself. But sometimes you don't need to sketch if a system is not that tricky though, right? Yeah. So anyway, so if you sketch that, you'll see the bending moment diagram, okay, which will look like, okay, this two at here. Okay, yeah. Okay, so once you get your bending moment diagram of these two at here, right? The next step is, okay, is to for the next step first is to basically pinpoint critical location. Essentially, is the locations that where we wanted to design, okay, and to come up with the minimum shaft diameter at here. Okay, yeah. So if I go back to this system here, it's usually pretty obvious. If I go back to the system, right? If I look at the critical location are typical locations related to where you have basically stress concentrations. So if you look at this particular system, there's a shoulder at here, the shoulder here, there's a key at here, there's a shoulder at here, there's another shoulder at here. So those are basically possible locations of interest to you, right? In particular, when you have a key, keys are typically have a higher stress concentration than the location of a fillet at the shoulder. Okay, so case location are usually will be the critical location that you will use to analyze. So this location here, that's where we will basically look at. Okay. Now if you look at the location A here, this is where the force is. So that's actually not too bad because this is where your moment starts, which is 0, right? So that we don't need to worry too much. The B location is a fillet location, but B location is so close to K location, and B location and this K location supposed to have the same shaft diameter. And as I said, the K location will typically, the KC location will typically be more critical than the fillet location. So we don't need to look at the B. We can simply just look at this location at here. That makes sense, right? If you keep moving further here, C location. Now you got to be careful, huh? It appears there's a supporting force here, but C location doesn't mean the C location has a 0 bending moment. Where is the 0 bending moment location? At both ends of the system, right? This is the end, this is the end. So C location actually has certain amount of the bending moment, and you need to analyze that. And because there's a step change over here, so C we need to do that. And D also has a small shaft size step change at here, and D happens to be just before the end of this shaft, right? The center of the sheave is the end of the shaft. So there's a very small distance over here. That's where your D is. So there is a small bending moment over there at the D location. Okay, and also there's a torque at here at the D location, right? Yeah. So that's why we also probably should also look at the D, because the D has a shaft size change at here. Okay. So overall, you can see for this system, I can look at this K location, the C location, and the D location. Okay, and in this system here, the part of the shaft at the two bearings, apparently they assuming the same shaft size. So if we can determine the shaft size at C, then we'll be able to determine the shaft size at the A location. Okay, yeah. So that's the idea here for this particular system, right? Trying to pinpoint critical location. So in our case, what we're going to look at is we're going to look at three locations. One is the K seat, okay, another is C, and the D location. Okay, so this is what we're going to look at. Okay, so maybe I should add one little bit data here just before we move on here. Sketch the bending moment and torque diagram, and I should have another thing here. Basically, you could either calculate or sketch the combined bending moment. Because we're talking about two-plane bending, right? So you need to combine the bending moment in the two planes into one single value here. So the first one here is in two planes. Okay, this is in two planes. So it has to be combined before you can calculate. Combine essentially here, for example, I decided to analyze the K state, the C, and the D location. So what we need to know is what is the bending moment at the K seat location, and what is the bending moment at the C location, and what is the bending moment at D location. Now the value over here should be the combined bending moment now. Okay, should be combined one. In my lecture notes, that example, it shows you basically the combined one, but you don't necessarily have to draw this out. You can, if you're just these three locations that you're interested, you can actually hand calculate just for the three locations only. Okay, yeah. So doing some calculation, okay, you can find that this MK6 location is this much of a bending moment. Here is this much. And here is this. Alright, so once you find the bending moment, right, and then basically we'll be using the three bending moments to calculate our stress, right? Yeah. And the other thing is, because this is fatigue loading, so the shaft is rotating. The bending moment, okay, is the force is a constant at here. The force is constant here, right? So in other words, for the shaft, what you're looking at is this MA, it's not 0, and this MM will be a 0. Okay, so that's what we call completely reversed loading condition, right? Completely reversed. And the values are listed here is basically is the amplitude value. Okay, so this is basically the amplitude value here. Okay. Yeah. Okay, so once you find the critical location now, and then step number 5, okay, is to find the stress now. Okay, to find the stress. But we're talking about actually designing it here, so it's actually we're not going to specifically find a stress. We need to basically find the diameter of the system here. So that's the next big step here. Find minimum, okay, shaft diameter. Okay, find minimum shaft diameter. Now, in order to do that, you have your handouts. Okay, I given a handout to you guys in the previous lecture. Here. Anybody doesn't have a handout? I still have a few copies of it here. Yeah. That's right. That's when you do design, you actually should try to avoid that from happening. So your KC location, there is a parameter. The KC location needs to be at least E/10 distance from the coder location. Yeah. So the prelet and the K, they shouldn't be combined. That's right. Yeah. Make sure they don't touch each other. Anyone need a handout here? No? Yeah. Go ahead. Okay, so I'll show you the formulas here, right? And this is the formula basically under a completely reversed bending and a steady torque. Right? That's the formula we're going to use. And in my question, I used which one did I use? Probably use the Gerber line in here. Okay, yeah. Anyway, so we'll use one of those formulas here. Okay, yeah. So if you look at the formula, right? If you look at the formula in here, on the side of the formula, what do we need to calculate? So we have MA, we have TM, which we already have it, but we do need what? We do need the fatigue stress concentration factor. We also need the fatigue endurance limit SE at here. So we do need these values at here, right? Okay, so that's what we need to figure out at here. Basically, under this step 1, step 5 at here. So that's basically figure out what SE equal to. Okay, SE equal to. Okay. So first of all, you have material SUT. Okay, it's so material in this question is SAE 1020. So SUT is 65. If you look at the and this is PSI, KSI. If you look at the table, then you'll find SUT and SY. So that basically means your SE prime is equal to 0.5 times SUT, 32.5 KSI. Okay, yeah. Okay, and then calculate SE. So SE, if you recall, is equal to KA times KB times KC times KD times KE SE prime, right? Okay. For this particular question, so the question here, I think it tells the surface is machined. So you can calculate your KA is going to be 0.893 for a machined surface. Okay, for the machined surface. And then the KB at here is a size factor. So if you recall that size factor depends on what? Depends on the diameter, right? Depends on the diameter of the shaft. But we don't know the diameter shaft, right? So we can't do anything. So we leave the KB as it is. So, but just know that KB is a function of the shaft diameter. And KC is the loading condition. So that will be just 1. That's basically the typical loading condition. Okay, and then KD is the temperature, right? So assuming room temperature in this question will be 1, and KE is the liability. So for 50%, which is a question given you already, 50% reliability, which is 1. Okay, yeah. So that's the parameters here. You substitute in this one the SB. The KB at here, we don't know what it is, right? So if you substitute in this formula, you get 25.1 d to the power negative, negative 0.107 here. Alright, so that's your SE. So basically, we cannot have a specific SE value yet without a minimum diameter, shaft diameter d. So in other words, your SE value, okay, your SE value is a function of the shaft diameter d. Okay, yeah. So leave it as it is. That's your SE. And Kf, Kfs. Kf is the fatigue concentration factor for normal force, right? Normal stress. And Kfs is the fatigue stress concentration for torsion. So we do have a bending moment and also the torque in this question. So we need the Kf and the Kfs, okay, for both components. Okay. Calculating the Kf, the formula is 1 plus Q Kt minus 1. Okay. And the Q is basically a function of the fillet radius. Okay. This is your Q at here, right? And Kfs is 1 plus Qs and Kts minus 1. And there's a similarly, there's a formula for the Qs, okay, for the Qs here. That's a big picture. That's how you can calculate this one at here. Okay. Now, to calculate the Q, right? To calculate the Q at here, we need the Newberg constant. Newberg constant is function of the material, so that's fine. That can be calculated once you have the material. But the Q is also depending on the notch radius R at here, right? So if the question didn't, especially at the beginning, when you start to design, you know, really you probably haven't decided on the fillet radius yet, right? Yeah. So what you can do is, so you can assume a very conservative, okay, assume a conservative fillet radius R, or notch radius. And conservative basically means it's a small number. So we can assume a small number 0.01 at here. And this is the first iteration, bear in mind, okay? This number here, you can actually definitely could be changed in a future stage. So this is basically the first iteration here. So once you assume in this one, then you can substitute. Then you'll be able to calculate this Q at here, just like what I showed here in my example. So calculate the Newberg constant, and then R, you will be able to calculate the Q at here, right? Yeah. And then similarly, you can calculate the Qs for the torsion. So these two numbers, with the assumption of a conservative R, and you will be able to get the Q and the Qs. Okay, approximately. Good. Okay. Okay. So coming back to fatigue stress concentration factor formula, I got a Q and a Qs. What about the KT and the KTs, right? And if you recall yourself, you know, basically the way to find a KT, KTs are based on a set of figures in Appendix A-5, Appendix 5, and that figures, you know, there's a whole bunch of curves, right? And the value of the curve depends on the ratio. For example, one side of capital D divided by the small d on the other side of the step shoulder, or it depends on the ratio between the notch radius R and divided by D, right? So, but we can't use that because we don't have the parameters yet, right? So what we have to do is, so basically for KT and KTs, okay, initially we have to start with conservative values here, okay? So essentially it's like a start with a guess, okay? The conservative values in the textbook in the previous lecture, I actually showed you a table here. So this is one of the table that you can use to start your KT and KTS. For example, if you consider shoulder fillet ratio R over D equal to 0.02, you can start your KT 2.7, KTS 2.2, and for a K-sit you can start with a 2.2, right? So this is a starting point you can start with at here. Okay, yeah. Now in this particular example, we start with even more conservative value. So we start, let's say, KT equal to 3.5, and KTS start with a 2.0, and then KT for the K-sit with a 4. Okay, so in this particular example, started with the even more conservatives. Okay, but as I said, or from the table 7-1. Okay, so not necessarily you have to always start with this kind of conservative here, but for this example I start with this one here. Okay, yeah. So once you have you start with this one here, then you substitute into the formulas over here. Okay, so now we can have our basically that the K-sit. Okay, we get the KF value for the K-sit is 2.5, and KFS value for the K-sit is 2.7. Okay, and for the C location, and the KF for the C location is 2.24, and the KF for the KFS for the C location is 1.57, and D location we get the same number as D location. Okay, yeah, so that give you the starting point. Okay, as I said, this is not the accurate description of the fatigue stress concentration factor. This is just the first iteration. Okay, yeah, just the first iteration. Okay, so once you get this step now, okay, then let's look at the shaft diameter formula at here. So basically, we need to choose a formula for our calculation, right? We need to choose a formula for our calculation here. Which one did I choose in this example? So it actually doesn't matter. Let me just show you one in here. So in this example, we use the D.E. Goodman equation. Okay, so use D.E. Goodman equation right here. Okay, so this is a D.E. Goodman, right? And this is the C at the C location here. So let's look at the C location. Okay. Yeah. So for example, right, this is a D.E. Goodman, general D.E. Goodman location. At the C location, we know that TA is 0, MM is 0. So the TA, so this term is gone. This term is gone. And we have our KF and a KFS calculated, so we can substitute over here. But SE, we don't know what it is, so basically you have a simplified version which is D equal to this one here. In other words, we get a sort of relationship like this. So D equal to an expression on the right side, which is function of D itself. So basically, what you're looking at is a nonlinear equation. Your D equal to a function of D, basically. Okay? Yeah. Then, how do I solve this question? How do I solve this? Right? So basically, you're looking for a solution. D equal to F of D. So what value of D will satisfy this equation, basically? Okay. Yeah. This one here, what you need to do is basically you need an iterative process to solve this, to solve the D here. Okay. So the idea is, okay, the idea here is to basically start with the value of a D, substitute here. So basically, start with a D value. Okay. Any D value. Actually, you can start with any D values. Mathematically, it won't make any difference. It will converge to a certain constant. But you can start with the D value here, and then let's say this is your D naught. Okay. Then you can calculate this, find a value after this starting value D, and then substitute back to this function again, and then get back to another D. So that's basically what we call the iterations at here. Okay. Yeah. I'll show you the Excel here, so you don't really need to calculate this by hand. This Excel here you can use to help you in terms of the calculation. So here's an example here, right? At the C location, that's the formula. So you can see here. So the start with a D. Once you start with the D here, then you can calculate the KB value, right? You can calculate KB value. So what do we start with? We start with the 0.5 here. Okay, we start with 0.5. With the 0.5, you can find the size factor KB, and then you can look at the formula for the S prime. You can find the SE at here, right? SE, and then using the right hand side, which is this formula. Okay, you look at this one. This is the formula for this. You can get the first results of the first iteration. So the first iteration coming back to the left hand side, and then substitute again based on this updated D value. Calculate KB, calculate SE again, and get another one here. So you see they actually converge quite quickly. At the end, it'll converge to 0.557. Okay, so converge to this much right here. Similar for the other location. You see I use the same basically same approach to do the calculation for the D. Okay, yeah. So that's the idea of iterative solving for the D at here. Okay, so iterative solving. So with this approach, okay, that's basically at the end here, and you will find 3D value, right? 3 critical. Find the D diameter values for the 3 locations. Okay, so you'll find that the critical, this is basically what we call the minimum, and then this from the results of it here, the minimum shaft diameter for the 3 critical locations here. Okay, yeah. So D1 equal to something, D2 equal to something, and then D3 and equal to something. Okay, yeah. So basically, you can draw a very simple diagram in here to help you. Let's see, this is the sort of the layout for okay. That's approximately this side is too big here. Okay. That's kind of the layout of the shaft that is here, right? So you have D2 over here, and this is also D2, and this is D1, and this is your D0, and this is the D3 location, right? The D3 location. Okay, and the bearings are at this location here, right? This is your bearings. Okay, it's bearing. Okay. Okay. So this is basically, I'll write down some results that are here. Okay. So let's say for D1, that's your K-seat location, right? D1, you have a K-seat over here. Okay, so the shaft diameter D1, that's the K-seat location. We find, okay, through that formula we find the minimum D1 is about D1 is 0.523. Okay, that's the D1. Okay. D2 we also find certain values over there. Okay. Okay. So this calculation, okay, this is based on, okay, this is based on formula. Okay, which formula? You know, Goodman equation, right? That's for example. Okay. Any formula, you probably come slightly different D, but this number here is from formula calculation. Okay, yeah. So does that mean we're going to have to take this number as the minimum shaft diameter then, right? So this is a D1 and a here. Okay, this is a D1. Okay, and let's leave it for now. Okay, let's look at the theoretical calculation for the D2 location. So D2 is the C location. Okay, D2 is the C location. C location, minimum number calculated, as you can show here, right? That's how much? 0.559. So minimum D2 equal to 0.559. Okay, yeah. And I left some space here because I'm going to add some contents at it here. Okay. And then let's look at the D3 at it here. So D3 is at the D location. So D location, if you calculate using formula, you get a minimum D3 is 444 inch. Alright, so these are the three numbers based on purely theoretical calculation, minimum value. Okay, minimum value here. But we have to make a decision, you know, basically based on not just the theoretical calculation, but also based on some other factors here. Okay, but for example, let's start from the C location. Where is the C? C location, basically it's this location here, and which has the same diameter as this side here, right? So C location basically is where the bearing is being mounted, D2. So in other words, what we have to do is we also have to look into the bearing catalog. So the shaft size right here has to be considered at the same time with the bearing catalogs, bearing ball size at here. Right? The bearing's ball size needs to be taken into consideration. So, for example, in this case, okay, we'll have more bearing selection details. But just say, let's say you selected a so-called 02 series bearing that has 15 millimeter. Okay, 15 millimeter. And 15 millimeter is approximately 0.5906 inch. Okay. And whether the bearing is suitable for this purpose or not, that's a different. We have to talk about that later when we are learning for bearing selection. Okay, that also needs to be calculated. So, but let's say you selected a 15 millimeter suitable bearing here. Okay, so if you look at this 0.5906, that's bigger than your calculated minimum value here, right? Which is fine, right? Because this is the minimum. So basically what happens, you're going to bump up this shaft size of C to a slightly bigger value. Another thing, just a heads up, is bearing catalog, okay, are typically given in metric. Okay, typically in metric. So what does that mean is you probably actually working on a problem that is in the US unit. Okay, so somehow we're gonna have to do a little bit unit conversion at here when you pick a bearing, basically. Okay, yeah. So in other words, for the shaft at here, so what we're gonna do is we will decide on D2 equal to 15 millimeter, which is 5906 inch. Okay, so that's a simple decision making based on the bearing selection. So now you got one location of shaft size determined, right? One location shaft size determined. So then you work, let's say, backward to D1 now. D1 is calculated to have a minimum 0.523. Now, if you recall in previous lecture, whenever you have a shoulder at here, especially the shoulder here carries a bearing, the bearing catalog often in time will actually give you the desired shoulder size D1. Okay, and for this particular calculation, we'll take a ratio D1 over D2 1.2. So the shoulder ratio generally between 1.2 and 1.5. Okay. So if I take this D1 over D2 equal to 1.2, so that'll give me a D1 equal to 1.2 times D2, right? And D2 we have decided, which is 0.5906. And that gives us approximately 0.7 inch at here. Okay, so 0.7 inch most probably is a normal size. It's the size in the appendix, the standard size. So I can take this as my D1 size. Okay, so D1. And now let's look at the D3. So I can use a similar analogy at here. So minimum calculus is this much, but I can use a similar ratio at here between D2 and D3 as 1.2. So D3 equal to D2 divided by 1.2. So which is 0.5906 divided by 1.2. That's approximately 0.5 inch at here. Okay. Yeah. And finally, there is also the D0, basically which location? The location here, right? Basically this location here, the biggest portion. So we can use this similar relationship. So D0 over D1, let's use 1.2. So D0 is 1.2 times D1, which is 0.7, and that gives me 0.84 inch approximately. Okay, 0.84. So D0, 0.84. You could basically pick D0 to be approximately 0.8 inch as a nominal value. Now you might say, why not pick a 0.9 or 1 inch, right? Yeah. Now, just for you to bear in mind is basically the D0 location is what? The D0 location is basically the biggest size location of the shaft, right? How do you manufacture this shaft then, right? Where is this shaft from? The shaft is probably machined based on certain initial size sample. So this is basically where the actual consideration. You go to a shop to buy a piece of raw material, and the diameter of the shaft you buy is the D naught, right? The D naught here. And you tell him I buy this length of the shaft. And then you go back and then you started to basically machining the shaft to give you this layout at here, right? So that D naught is essentially the original size of the shaft, right? That original size needs to be off the shelf, okay? So slightly smaller than this 0.8, that I think that should be okay, right? So this is basically from commercial, off the shelf, right? Okay. So that D naught value. So with all of this determined value added here, okay, the last step, number 6. Okay, the last number 6 step is recalculate based on the selected values. So now you have a selected value D. Now you can go back and then calculate what is the actual safety factor, right? For the safety factor. There's factors at the different locations. So that's the final step you should do. There is a possibility that whatever you decided actually may not work, but mostly it'll work because you see the computation in here are really based on a very conservative values, right? Initial values. So the values that you calculate here, 99% chances it will work when you do the final calculation. Okay. Yeah. Now this final calculation, basically, when you do the then dollar key F, key FS, they're not going to be the values from your initial guess, the conservative value anymore, right? You will be able to basically, once you have the D, you will be able to get the actual key F, key S. So this is going to be actual now, right? Going to be at actual values. Okay. So that essentially is the typical process on the shaft design. So I just want to make a few comments at here, or serving as a sort of a summary at here. Okay. So bear in mind that your first iteration, right? First iteration give you is the minimum value. Okay, that's something you have to bear in mind. And the shaft size, right? The shaft size are not just based on the theoretical minimum value. It should also be based on gear or the bearing ball size. Okay? And if you pick a commercially available gear and that gear maybe has a decided ball size already, which you can't change, right? So if you can't change, then you need to bump up your shaft size. So that's basically another thing, because your shaft will carry the gear, right? And shaft will carry the bearing. So the commercially available size, ball size, should be considered when you make a decision on the shaft size. And there is also the suggested value, okay? Suggested value for shoulder size, okay, from bearing catalog. So that's a location that you wanted to really carefully examine. What is the suggested value of from the bearing catalog? Because that's how the bearing manufacturer suggests how you can locate the bearing onto the shaft, right? Yeah. So that information from the catalog actually sometimes plays the deciding factor there. Okay. Yeah. And you also need to consider stock size, okay, or available size. Basically, that's the D naught. Okay, that's the D naught value, right? And I have been using this ratio at here as 1.2, but it's between 1.2 and 1.5. Okay, this is some empirical values that you can make use of, okay, to help you to calculate, especially in the first iteration there, okay, first iteration. Any questions? Yes.
So for the recalculation there,
yeah.
would that be the be selected in
Yes. Yeah. You can stay with 0.01. That's fine, right? Yeah. But you can think. You can imagine you have R divided by the actual D. Then you can go find the actual KTS, right? So basically those are. Then you can calculate the actual KFS, basically, right? Yeah. Is that good? So that's the typical process, for shaft design. You should expect certain level of iteration back and forth. So there's already back and forth at here, right? The other back and forth is you know, especially if you have two students working on two different part of the project. So I'm working on the bearing, and he's working on a shaft. So the guy working on the bearing selected the pair of bearing already, right? And then they give you to the person working on the shaft. Say, okay, here's the bearing I selected. And then say, okay, well, your bearing has this much ball size, which is different from what I decided upon, right? Then what do? Then the one designing for the shaft needs to be recalculated, right, based on the new information, essentially. Okay. Yeah. Which brings to the next one. I want to use the rest of the time just to talk about the design project. Okay. Yes. Yeah. Okay. In exam, you actually probably won't have this kind of complicated situation. Yeah. It will be much simplified. Basically, for example, I'll give you what the ratio is, right? It's along the line of iteration for sure. You know, I'll give you a certain condition, but you have to iterate a couple of steps to end up with a D value, just like what we did in using the formulas like this. So basically, the same idea using this formula, but it will be much simplified version by some values already given, right? But of course, your SE value, for example, still depends on the size factor KB, right? So KB depends on the diameter. So first step, putting a value for the D, calculate KB, calculate SE, and then get a D value. Put it back into this equation again, find another D value, couple iteration, then you settle down at a constant converged value, right? That's the idea of it. If I do exams for shaft, actually, as a matter of fact, there will be a question in the final for the shaft design. It'll be basically a question along that type of that direction. Okay. Yeah. Any other questions? Okay. Okay. So I'll use the rest of the time just to talk a little bit about the design project. Okay. I have uploaded a couple documents at here. Okay. This document, if you prefer 1 minute reading, this Excel is probably the easiest location to locate some of the key design requirement, design limitations, and the design options that are here. Okay. You're already given the amount of horsepower here, and also the life number of hours. Okay. And you're designing for a gear ratio of 3.5. Where did they say 3.5? I remember 3.5. Where's my 3.5 here? Oh yeah, so this is from input speed and output speed. You divide it by each other, you get a 3.5 basically, right? Yeah. So the gear material is restricted to cast iron 3040 and steel. Okay. The steel, you should look at the figure 14-2 for the bending stress number, 14-5 for contact stress number. And also there's a restriction to the maximum center-to-center distance. Okay. In the shaft, the materials choose from only between the amount of 380 here. Okay. The shaft has a design fatigue safety factor at least 2.5. Okay. The case has a safety factor of 2, and the bearing has a life. So we'll look at it later here. But for now, you can very well start the shaft and then the spur gear design part of the projects already. Okay, yeah. So there is a formula. There is an Excel template given for the spur gear. You can use that template to help you do the computation, right? The bottom line here is, there are a lot of unknown factors at here that you need to decide. For example, if you design a gear, so what's number T size should you use, right? And what will be the diametral pitch that you should use? Okay, so these things that you need to decide upon. So how you decide upon these things here is purely up to your group decision here. So you can decide upon using low cost or smaller size. Okay, and you could also just basically randomly come with a set of numbers that works, right? But the more systematic, the more rational, the more basically comparisons that you given in your report, then the better grades that you will have essentially. Okay, and that brings to my basically evaluation of the design project. There are grades breakdown for different sections of design. Okay, there's also part of the grade given to the modeling and the writing. Okay, so I have another rubrics I think uploaded basically for the grading of this report at here, and this rubrics essentially designed to match these so-called graduate attributes. Graduate attributes, there's a design process, there's also the quality of the writing, there's also how you use the engineering tool. Okay, it's basically associated with the sections of your report, right? Do you have a solution assess? Essentially, sometimes I have read some reports. There's no comparison from the beginning. Come up with a number, works, next, works, next, works. Everything works. That's it, right? Yeah. Not that it's not okay, but why, right? If you present the customer, not just you giving them a number that works, you have to give them a sort of analysis why it works, what you have compared with, right? So that's the assessment part, huh? Yeah, it's essentially there's different weighting here. You can take a look at the biggest weight is on the design process here, right, in the design portion. Okay, yeah. Okay, so for the solid modeling part, you could use either softwares, CAD, SolidWorks, or AutoCAD Inventors, also free. Okay, either one's fine. Okay, and you should have a gearbox, the casing for the box. I don't need you to design very fancy ones. Just as a complete, just design some sort of box to enclose these gears. Okay, yeah. But you should have some of the details. Basically, I will open up your file to look at it. How well your assembly is. Is there any errors in terms of sometimes you could just constrain assemble it, but in actual you can't actually assemble it, right? So there should be a reasonable, basically a consideration given to the assembling process for the system. So you have a gear, you have a bearing, how you locate the gear on the shaft, both radially and axially, right? how you locate the bearing on the shaft, both radially and axially. So that type of small considerations, right? Yeah. So make sure if you cover all the details, you get the really good grades for sure, okay? But otherwise, the majority of the portion of the grades will be on the design portion, the computation, the iteration of the design process, okay? Yeah. Yes?
Can you throw it into like an Excel document and then do iteration based on the
Yes, you can. So I have seen some group basically create another table, right? So another table basically results from, you use the template. You calculate, plug in this value here, calculate, plug in this value. So you create a table, essentially it's like comparison between different combinations of parameters. Let's say one group, I choose 70, 22, the number of T's, diametral page 4, material, this one. It worked, right? And you pick another one, another combination. It doesn't work. That's fine. You put it there, right? So there should be a certain level of basically iterations shown in your design process, not just one iteration. That's it. Right? You may have done something, but if you don't present it, then I wouldn't know, right? Yeah. So that's what when I do the marking, and I will look at this kind of level of the details there. Okay. Yeah. Any questions? Final words. I would strongly recommend, even though I know that whatever I say won't work, that you have to start now and start early, because I know you have a lot of projects at the end of the term, right? Try not to cram everything until the end of the last week. Okay. Start early and save yourself some time. The good thing is our final exam is pretty late, so you have some leverage there, but you do have other courses to pay your attention to, right?